All right. So last night I left off on reading this blog post on the sorry state of dynamic libraries on Linux. It's from 2012. Covers some of the reasons why position independent code is suboptimal, because it goes through the procedure link table and the global offset table for allowing for interposition, um, or sorry, interposition. Yeah, I think that's the right word. Basically, intercepting by doing everything indirectly through the global offset table and procedure link table. Yeah, you can see here they're going through the PLT and the GOT PCREL RIP. So that's the main complaint, I think, here. But I wanted to read the entire article here. So let's start from the existing solution. So we know the problem is that this is like if you're not using position independent code, it's very optimal. You do a single call. So this is the code that we're compiling here. We do a single call of the external function, and the linker updates the location of this function once it's resolved at link time. And so it's just a direct call to the location. So this call instruction is actually patched out with a relocation. Then the external function here, we're getting the this bit of a syntax that I'm not super familiar with. So it looks like GNU registers, or sorry, AT&T registers. So this is going to be from left to right, which makes sense because we're taking the address of the external function here and storing it into external variable. I actually don't think you need the ampersand here. I think C allows you to just take the external function name here, and it understands, okay, that's a pointer to a function. That would mean the external function, yeah, is resolved at link time. Yeah, I don't think you need the ampersand here syntactically in C. Anyways, we're taking that address of the external function and we're storing it into the external variable, which is relative to the instruction pointer. So this is still position independent because it's addressing is relative to the instruction pointer, but yeah, it's relative to the instruction pointer, but it's not going through the global offset table or procedure link table. So this is about as optimal as you can get for encoding these two statements into AMD64 assembly. And that's enabled because we're not explicitly using pick or pi flags, which are now default, I believe, in all compilers on Linux. So I'm curious if this has actually gotten fixed. Some of this inefficiency has gotten fixed. Or if they're leaving it in as part of the design of position independent code flag here. So this is the position independent code flag. So we call through the PLT, which isn't horribly inefficient. It's like one level in direction, but it is less efficient than just calling the function directly. And then we have 3 MOV quad words instead of 1 because of the limitations of computing addresses, relative addresses here. So the first thing is we have to say get the external function at the GOT PC relative. So this is relative to the program counter. That's what that PC relative means. And of course we compute it based off the instruction pointer here, and we store that in. Instead of going directly to RIP, which is interesting that instead of going directly to the location external variable relative to RIP, so this instruction here is encoding the destination address, which is external variable relative to instruction pointer. So we have to figure out what the address is and store that in our RAX. And then we have to figure out what the address is of the function and store that in RDX or any other general purpose register. And then we can dereference RAX and store RDX into RAX dereferenced. So that will put that value into that location that's being pointed to from RAX. And I think the reason they mentioned the reason why you have to do 3 instructions here is because basically you can't encode all of this PC relative stuff for the source and destination in a single x86-64 instruction because it exceeds the yeah, here it is. Such instruction would be at least 17 bytes long, which is 2 bytes longer than the maximum instruction length. So basically, the instruction set architecture does not have an instruction that allows you to both do got relative to instruction pointer resolution for the source and the destination. So yeah, that's the reason why I have to do 3 instructions here. Whereas this one, it's like, okay, external function, store into a destination that's relative to the instruction pointer. Okay, so let's go down here, existing solutions. Let's continue reading from here. Existing solutions, partial solution for private symbols. When developing your library, if you know what certain symbols are private and will never be used by any other library, you have an option. You can declare their ELF visibility to be hidden, which has 2 consequences. The clear one is that the linker will not add the... Why are people going through my garbage right now? Oh, okay. Sorry. People outside hanging around my garbage cans. Okay, when developing, okay, you can declare their ELF visibility to be hidden, which has 2 consequences. The clear one is that the linker will not add the hidden symbols to the dynamic symbol table. So other ELF modules simply cannot find them. If they can't find them, they can't steal them, and if they can't steal them, linker does not need to produce a PLT stub for the function call. So the call instruction will be linked to a simple direct call as the executable in the first part has been. The other consequence is an optimization that the compiler does, since it knows that the external variable cannot be stolen. It does not need to address the variable indirectly. The generated assembly becomes the call directly external function at PLT. So it's still going through a PLT, which if we go up here, we didn't have. And then the MOV, again, you need 2 instructions probably because you can't compute source and destination in 1 instruction. So you could just compute the source, store it in RAX, and then store RAX into the destination. The .o file will still contain 3 relocations. However, note that the getting of the address of the external function is still done indirectly, even though the compiler knows it cannot be interposed. That means the linker will still generate a load time relocation for the dynamic linker to get the address of that function. Fortunately, it's a simpler relocation since the symbol name itself is not present. If there's a reason to get the address indirectly like this, I have yet to find it. Yeah, it seems like a needless indirection there. Going through the PLT and the GOT, it's probably just like the simpler implementation for position independent code. Partial solution for public non-interposable symbols. If your symbols are public, however, you cannot use the ELF hidden visibility trick, but I think the hidden visibility trick is to make it static. But if you know that they cannot and will not ever be stolen or interposed, you have another possibility, which is to tell that the compiler to the compiler and linker. If you declare a variable with ELF protected visibility, you're telling the compiler and linker that it cannot be stolen, yet it can't be placed in the dynamic symbol table for other ELF modules to reference. You just have to be absolutely sure that they will not ever be interposed, because that will create subtle bugs that are hard to track down. That includes access to those symbols by position-dependent executable code. Like we did in the first section, the GCC syntax attribute visibility protected works, that's interesting, works in ELF platforms only, whereas the one with the hidden keyword is known to work in non-ELF platforms too, like macOS, IBM AIX, XCOF. Another way to do the same is to use one of the two linker options, bsymbolic and bsymbolic functions. They do basically the same as the protected visibility. They keep the symbols in the dynamic table, but they make the linker use a symbol inside the library unconditionally. The difference between those two options is that the former applies to all symbols, whereas the latter applies to functions only. The reason why bsymbolic functions exist requires looking back at the executable code from the first section. While the variable reference required a copy relocation, the function call was done indirectly through the PLT stub. A variable can be moved, but moving code isn't possible, so the executable code needs to deal with the code being elsewhere anyways. For that reason, it's possible to symbolically bind function calls inside a library without affecting executables, or so we thought. The problem we discovered last week deals with a situation where you treat a function as a data reference, taking its address. As we saw in the first part, the linker will resolve the address to the function to the address in the PLT stub found in the executable, but if you symbolically bind the function in the library, it will resolve to the real address. If you try to compare the two addresses, they won't be the same. Interesting. Proposed solutions. Some of the solutions I propose are ABI and binary compatible with existing builds. Some others are ABI incompatible and would require recompilation. Unfortunately, the best solution would require some source incompatible changes. Still, all the changes below are giving a bit of optimism to libraries, a bit of optimization to libraries by making executables less optimized. Use the PLT and function calls should rest only with the linker. As you saw in code generated for the library, with fpic, the compiler decided to make the call indirectly by adding @plt to the symbol name. Turns out that the linker doesn't really care about this and will generate or not the PLT stub if needed. If that's the case, the compiler should not make a judgment call about where the symbol is located just because of fpic. Function addresses should always be resolved through the GOT. Function calls already require a pointer size variable somewhere in the relocation to be made to point to the valid entry point of the function being called. What's more, taking addresses of functions is a somewhat rare operation compared to the number of function calls across ELF modules. That being the case, we can take a small hit in performance, and the loading of a function address should happen via the GOT and position-dependent code executables, just like it is done for position-independent code. The benefit of doing this is that the function address we load will point to exactly function's real entry point instead of the PLT stub. When we call this function, we avoid the doubly indirect branching we found earlier. The PLT stubs should use a regular GOT's address if it exists. If a given function is both called and its address is taken, the PLT stub should reference GOT entry that was used for the taking of the address. The reason why it isn't already so, I guess, is because the entries in the GOT PLT section aren't initialized with the target function's address, but the local module's function receiver. This trick allows for the lazy resolution of functions. They are resolved only the first time they are called. I wouldn't ask for all functions to be resolved at load time, but if the address of the function is taken anyways, the dynamic linker will need to resolve it at load time. So why waste CPU cycles in a function call if the address was already computed already? Copy relocations should be deprecated. Instead of copying the variable from the library into the executable, executables should use indirect addressing for reading variables and writing to them, as well as taking their addresses. One benefit of doing this is avoiding the actual copying. For example, for read-only variables, they may remain in read-only pages of memory instead of being copied to read-write pages found in the executable. The big drawback of this is that the indirect addressing is a lot more expensive since it requires 2 memory references, not just 1. The next suggestion might help alleviate the problem. The linker should relax instructions used for loading variable addresses. This is a suggestion found in Intel Architecture 64 ABI. The compiler generates instructions needed to load the address of the variable from the GOT and then uses it as it needs to. If the linker concludes by whatever means the protected or hidden symbols the use of one of the symbolic options, or because this is an ELF application and the symbol is defined in it that the symbol must reside in the current ELF module, it can change the load instruction into a register to register move or similar. For the x86 64-bit case, the instructions the compiler generated were external variable add GOT, PC relative RIP, RAX, RDX into RAX. Okay. By changing one bit in the opcode from the first instruction with no code size changes, we can produce the LEA instead of MOV quad. Interesting. The x86 instruction LEA means the load effective address. Instead of loading 64 bits from the memory address and storing them in the register, that instruction, the address it would have loaded the register from. This isn't as optimized as the original code found in the executable for two reasons. It requires two instructions instead of just one, and it requires an additional register. It's possible to generate an even more efficient code if the assembler leaves a 32-bit immediate offset on the second MOV quad instruction, making it 6 bytes long. This extra immediate would be of no impact to the original code besides making it longer, but it would allow the linker to optimize the code further. The original would be this, and it would get relaxed to that. That's a no-op, right? That is, the first 6-byte instruction is resolved as 6-byte NOP, yeah. Whereas the second 6-byte instruction executes the actual store with no extra register use. The compiler cannot know that the register will be left untouched, but at least there is no dependency between the two instructions that might cause a CPU stall. The same applies to other architectures too. The full FPIC code on ARM to store a value from a register into a variable is the following. If the linker can conclude the symbol must be in the current ELF module and cannot change, may be able to avoid the extra load, the middle instruction, by changing the code to be so-and-so. Unlike x86, the ARM instructions cannot be optimized further since the immediates encoded in the instruction have limited range. The linker should relax instructions used for loading addresses similar to the above, but instead looking at function addresses. The original library code is MOV quad word external function at GOT PC relative into RDX, but it can be relaxed to external function RIP RDX with ARM. The original code, okay, I don't want to look at the ARM stuff. Okay. There should be a way to tell the compiler where the symbol is. We're already able to tell the compiler that a symbol is in the current module with the hidden visibility attribute. We should be able to tell the compiler that we know that the symbol is in the current module, but export it as well as that we know that the symbol is in another module. I would suggest simply using the existing ELF markers and being explicit about them. So these are ELF markers. I'm not familiar with these. Hidden, protected, and default. And decal spec DL import. Interesting. Symbols in the ELF module are not exported, equivalent to Windows no decoration. Symbols in the ELF module is exported, equivalent to Windows decal spec DL export. And then default symbol is in another ELF module, which is decal spec DLL import. It also applies to symbols that must be overwritable according to the library's API, like C++'s global operator new. Considering the other suggestions, we know the references to symbols with default visibility can be relaxed into simpler and more efficient code in the presence of one of the symbolic binding options. That means that we can use the default visibility for cases of uncertain symbols. Getting there. Some of the solutions I listed are already possible, and they should be used immediately in all libraries. That is especially true about the use of hidden visibility. A library without exception should make use of this feature. In fact, since this option was introduced in GCC 4.0 7 years ago, many libraries started using it and are now good citizens. They access their own private data most efficiently. They don't have huge symbol tables which impact lookup speed and don't pollute the global namespace with unnecessary symbols. Other solutions are not possible to implement yet. The solution I personally feel is most important to be implemented first is that of the ELF executables. They need to stop using copy relocations, and they should resolve addresses of functions via the GOT. Only once that is done can libraries start using the protected visibility and generate improved code. This implies changing the PS API for the affected libraries, which may not be an easy transition. An alternative is to using the protected visibility is to use the symbolic binding options. The code relaxation optimization would come in handy at this point to optimize at link time the code that the compiler could not make a decision on. Unfortunately, those options apply to all symbols in a library, so libraries that must have overwritable symbols need to use an extra option dynamic list and list each symbol one by one. Using fpi, the compiler option fpi tells a compiler to generate position independent code for executables. This is what I've been playing around with. It is similar to the fpic option in that generates position independent code, but it has the added optimization that the compiler can assume none of its symbols can be interposed. With executables compiled with this option, copy relocations and direct loading of function addresses aren't used. This solves the problem we had. Therefore, compiling executables with this option allows us to start using some of the optimization I described before. Unfortunately, as the description says, this option also generates position independent code, which can be less efficient than position dependent code in some situations. My preference would be to have position dependent code executables without the copy relocations. However, there is an added side effect of this option. It defines the __pick macro, whose absence can be used to abort compilations for libraries that have transitioned to the more efficient options. Further work and further reading, I highly recommend Ehrlich's Drepper's How to Write Shared Libraries paper. His recommendations did not go as far as suggest changes to ABI like I have, but he has many that library developers should adhere to, regardless of whether my recommendations are accepted or not. For example, using static functions and data where possible to avoid arrays of pointers are recommendations I have made to many people. Other work necessary is to improve pre-linking support. Shared libraries are position independent, but they can be pre-linked to a preferred location in memory. One optimization I have yet to see done is use the read-only pages of pre-linked data when the library is loaded at that preferred address, the data rel RO sections. All right, let's, I don't know why, but I assume this is like not a dude that wrote this, but it might be. Yeah, it's a dude. Okay. I don't know why in my head I was thinking that I was a woman that wrote that. Okay, I understood maybe like a solid 10% of this, to be fair. Like I don't claim that I fully understood all that. All right. And they recommended this thing, How to Write Shared Libraries, white paper. But I'm not really like a white paper reader typically, especially dated stuff like this. I wonder how it looks like it got an uptick, or at least in scrapes recently. And I should be able to link directly to the PDF here, right? If it's still being served here. Can I not? There you go. Yeah. This might be a good paper to read though. So far I'm like, okay, I would get some value out of reading this. Yeah. Okay, get to some C++. I think I would get value out of reading this. This is page 10 out of 40 something. Okay, constructors which are in C. I forget what DSOs is. Where's DSOs? Oh, just shared object. Okay. Where was I? Here? Yeah. So these are the actual recommendations here. Data definitions, what you should do there. Export control. Use static. Define global visibility. Define per symbol visibility. Define visibility for C++ classes. So this is C++ stuff. Use export maps. Oh, I wasn't familiar with this export map thing. Export symbols. Avoid using exported symbols. Using aliases. DF symbolic. Shortening symbol names. Choosing the right type. Pointers versus arrays. Arrays of data pointers. Forever const. Arrays of function pointers. C++ virtual function tables. Improving generated code. Increasing security. Simple profiling of interface usage. Maintaining APIs and ABIs. Definition stability, API versioning, restricting exports, handling compatible changes, GNU, handling compatible changes on Solaris and compatible changes, using version DSOs. This is what I've seen in all the GNU stuff, is that they use version DSOs, and I wasn't really familiar with how they actually manage that, so it might be interesting to read this. Inter-object file relations, counting relocations, some source code, automatic handler of array of string pointers, C index. What is this? Oh, it's just an index. This Drepper guy, I think I've heard of him before. Yeah. He writes a lot of white papers here. Ulrich Drepper. So researcher at Red Hat. Works on Good News C. Okay. All right, I'm gonna take a quick bio break here, and then be back. I'm gonna read more about Early Strepper. I might drop his white paper into my reading queue, and then we're gonna pop the stack on some of this stuff and try to get back to reading our book this afternoon. But yeah, I'll be right back. Okie dokie. I'm back. Early Strepper. Let's learn about this dude. Oops. Okay, so someone on Hacker News isn't a big fan of his. Let's get the context. So this is glibc, a bug and a joke. Back in 2011. This story and the story about the change in memcopy that broke Flash on Fedora. This is dated. Gives me a really bad impression of the people that maintain glibc. Seems like they really don't welcome comments and contributions. It's not people, it's just early, yeah. It's Googling, and this appears many of his decisions, which might be considered rude or not getting it, are actually a result of his philosophy of free software development as outlined here. Poor herd. Even the GNU guys are not crazy about it. Okay, I don't really want to read much more about this. His main interests are in areas of low-level technology like machine and processor architectures, programming language, compilers, high performance, and low latency computing. In addition, he is interested in using statistics and machine learning to perform analysis of programs and security of applications in OS environments. Boop. Seems like he has a lot of really good papers. What is this website? A magazine about programmers, code, and society written by and for humans since 2018. I feel like this model, which is certainly taught broadly, is so outdated with position independent executables. Basically, this model is like a lie. Yeah, I mean that's just how it is with PIE. And most binaries on Linux now are PIE, so I feel like this model needs some updating.
Memory management is vital for any programmer seeking to understand their program flow or optimize performance. It's often quite beneficial to know the anatomy of memory, how the operating system manages memory, and how memory is accessible to us as C programmers. The memory that is assigned to your C programs can be split up into different segments. Each segment is designed to hold a different kind of data. Let's quickly take a look at the anatomy of this segmentation, and then we'll come back and discuss each segment in more depth.
He's probably talking about like segments in this concept of like text and data, RO data, BSS, stuff like that. That is more related towards actually writing programs in C and assembly and C++, and having those programs compiled into object code and linked using segment data. Or is it section data? It's section data. Segments, he's talking about segments. So there's segmentation, which I believe is like a older form of memory management in AMD or in Intel CPUs. But he's probably referring to segments like program headers in an ELF binary, that concept of segments, which is basically regions of memory that have different protection flags. And are mapped by the loader, the dynamic loader at runtime, or by the Linux kernel. think that's what he's talking about here. Let's see.
Broadly speaking, the memory can be divided into a text and a data segment. The data segment is then further divided into static data versus non-static data. Static data can be grouped into initialized versus uninitialized. Finally, dynamic data is divided into two different data structures, the stack and the heap. This leaves us with 5 distinct segments, and the all too familiar memory diagram. So let's take a closer look at each one. First up is the text segment, which is also commonly called the code segment. The text segment contains the instructions for executing the program. This segment is read-only, so nothing can change the instructions of the program while it's running. It's also of a fixed size, and is read directly from the executable. This is also typically the section that stores any literals present in your code. Next, we'll discuss static memory, which is divided into initialized versus uninitialized data. The initialized data segment, sometimes abbreviated to just the data segment, holds initialized global and static variables. These are globals and statics that have set values in the code. This segment is also read directly from the executable and is fixed in size. This segment is read-write accessible, meaning the data in this segment can be modified. The uninitialized data segment, usually called the BSS segment, stores uninitialized globals and statics. BSS stands for block started by symbol. The assembly directive BLK, or block, initialized a block of memory to 0. And as such, data in the BSS segment is initialized to 0. But hang on, if you're just going to initialize it to 0 anyway, then what's the point of splitting it into initialized versus uninitialized data? Why not just store it all in the initialized data segment? Well, consider a case where there's a global array, like this one, taken from my current chess engine project. This is a pretty massive array, over 100,000 elements. Remember that the initialized data is read directly from the executable, meaning that if this array were to be stored in the initialized data segment, all 100,000 zeros would have to be written in the executable with it. The BSS segment, on the other hand, can just store the size of the array, and the zeros are implicit.
This is pretty basic stuff here.
Moving on, we'll discuss the heap segment. The heap segment, unlike the other 3 segments, is variable in size. It can grow and shrink as the program runs. The cool part is that you, as the programmer, are able to decide how it grows and shrinks. You do this by using functions like malloc or free in C, and new and delete in C++. The downside of this is, of course, the potential for memory leaks and other memory errors if you don't properly manage it. Nonetheless, the heap is useful for handling dynamic data structures like linked lists, whose sizes cannot be determined at compile time. Finally, there's the stack segment. The stack segment is the segment that manages function calls, local variables, and arguments. It's called a stack because it mimics the stack data structure, where things can be accessed only from the top. This gives way to the LIFO acronym, or last in, first out, when describing the operations of the stack. Think of it like a stack of dinner plates or a stack of books. The last one placed down is the first one picked back up. When a function is called, its local variables and arguments are pushed onto the top of the stack. The location of this new data is kept track of by the stack pointer. And when the function returns, its stack frame is popped from the top of the stack. Well, that's a wrap on memory segments. I left out a lot of the details in order to hopefully provide a succinct but still useful overview. If you're curious for more detail, I would recommend looking into each segment individually. Thanks for watching, and take care.
Well, that wasn't very helpful. Just a casual introduction. I wanted to see if this is going to be useful for me to read. It just says Ryan Baker as the title, and it's by this Adrian guy. He's writing about Christopher Nolan and Memento and Oppenheimer. This is the video I clicked on. Video the cue movie hits a chord. Remember, provides a simple visual interface to understand the major segment. I feel like this is a little bit too, how do I say this? Oh, there's a deer out in my driveway. Casual deer hanging out in my driveway. Hey, don't eat my... I guess he's eating my weeds. Yeah, I hope he eats the weeds. Looks like he's eating weeds. All of the intricacies of the subject of memory management. Blah, blah, blah. Let's maybe try another one here. I guess
Keyword is perhaps one of the most.
Let's pull him up on YouTube and maybe do a sub here. All right, Ryan Baker. Let me pull him up here on my personal YouTube. Ryan Baker, YouTube. That is not the Ryan Baker I'm looking for. YouTube Music. Not that guy. There's a lot of fucking Ryan Bakers on YouTube. What is this video? C++? Maybe if I search for that, he'll show up. Yep, there he is. He only has... Oh no, he has a couple videos here. Looks like he hasn't published in a year. Oh well, I subbed to him anyways. Let's see what he says about C++.
Words for beginners in C++. There are a few reasons.
Actually, you know what? I don't want to engage with C++ stuff right now. This white paper is something that I'd be interested in reading. What every programmer should know about memory. Yeah, this thing here. When was it published? Kill that. Kill that. Kill that. Jump to learn log. Vim. Papers. Alright, and then what was the other one here? Yeah. Why does that not copy? Is that some copyright thing? Jesus Christ. How to write shared, oops. There we go. Come back to that. Did you not link to this? Nope. Maybe? Here you go. Are these guys actively publishing here? Yeah. I really do like clean grapple. That ain't the same, bro. First edition, second edition. Hey, sorry, Mr. Chat there, Cyber Dark Light. What's going on? I'm just going through a bunch of rabbit holes with different books and papers and blogs I want to read. And this book is called What Every Engineer Should Know About Software Engineering. And I'm just doing a scan of the table of contents to see if it actually would benefit me. And I think it might. I mean, it's not like a huge book. If I look here, it's only 362 pages. I'm not familiar with the authors. I've always been more of the bits and bytes type software engineer than the architecture type engineer. I feel like architecture can emerge out of necessity instead of being something that predates the implementation. And there are other books in architecture I'd definitely read over reading this one for architecture alone. Okay. I'll put it on my list. What every engineer should know about software engineering. A lot of that is going to be review for me, but it doesn't hurt to do some review. And books like this that collect like a huge, broad section of knowledge and properly define terms really eliminates ambiguity in your thinking about different ideas that you may have encountered but you haven't really like spent time grappling with. And that's for sure like there's stuff in the index that I definitely feel like stuff that I'm familiar with that I've encountered in my career but I haven't really spent time grappling with. So having the like all the terms properly defined and having pre-thought out lines of reasoning about these ideas I think would be helpful to load into my brain. So yeah, I'll go ahead and put this on my list of books, which is growing rather long. All right, when you start popping the stack, I keep on going deeper. All right, let's continue reading here. This book in particular is a part of a series of CRC Press about precisely what every professional in a particular branch of engineering should know about some other subject. In the same vein, we cannot omit a mention to 97 Things Every Programmer Should Know, edited by none other than Kelvin Henley, and 97 Things Software Architects Should Know, the one edited by Richard Monson Haffel. Each of these two books are entirely worthy of their own entries in this section. $250 pager. 97 Things Every Programmer Should Know. Act with prudence. Apply functional programming principles. Ask, what would the user do? You are not the user. Automate your coding standard. Beauty is in simplicity. Before you refactor, beware the share. The Boy Scout rule. Check your code first before looking to blame others. That's one that you'll learn on your own, I feel. Choose your tool with care. Code in the language of the domain. Code is design. Code layout matters. Code review. Code with the reason. Comment on comments. Comment only what the code cannot say. Continuous learning. Convenience is not an ility. Deploy early and often. Distinguish business exceptions from technical. A lot of deliberate practice. Domain specific languages. Don't be afraid to break things. Don't be cute with your test data. Don't ignore that error. Don't lean. Oh, these are all the 90. Wow, okay. This might be fun to pick up because it might be little bites of knowledge that you can like kind of, it might not be something that I'd want to like sit down and read cover to cover. But one that I can just like crack open periodically and like do some reading on. Small little bites. Stand up. What is this? Oh, and these are different authors too. Okay, we'll add them to the books list. Which would be please just stop doing that? I hate websites that do freaking like chat pop-ups and shit. Oops. Alright, we'll kill that one. Grab this one. Look at how many fucking pop-ups there are in here. It's crazy. Okay. Alright. But as usual, I digress. Let us return to Mr. Drepper's paper, the subject of this month. The paper provides an explanation with details of how memory works under the hood, how programmers use this knowledge to write better software. The paper is organized in 8 sections, starting from the hardware basis of memory and including SRAM, DRAM, bus latencies, explaining why DRAM and the dominance of is a dominant form of main memory. Guess what? The main real reason is cost. These explanations are sprinkled with very interesting bits and pieces of computer architecture history, even though most computers for the last several decades have used the von Neumann architecture. Experience has shown that it is of advantage to separate the caches used for code and for data. Intel has used separate code and data caches since 1993 and never looked back because of different access patterns. I think that'd be the main reason why you do that. And Intel does have like a L3 that's like shared between code and data, so it's not all separate. The reader is then pushed into the realm of CPU caches, starting from the reason of their existence, then diving into cache levels L1, L2, L3, and their historical evolution, and even showing how Intel and AMD implemented their caches differently. Because yes, that had a perceivable effect in the performance of the computers you could buy at the turn of the millennium. On-goods Drepper into virtual memory, hyperthreading page tables, memory management units, non-uniform memory access, direct memory access, direct cache access, and many other acronyms that might have probably already encountered, particularly when shopping for CPUs, motherboards, and other computer components. This is your chance to finally understand what this is all about. Needless to say, this paper is particularly interesting for developers working in C, C++, Zig, or even Rust, where knowledge about memory layouts and performance can make or break a whole project. In particular, I think I'm thinking about those developers. Mr. Drepper provides an introduction to Valgrind and its associated tooling, the cache grind tracing profile, and the massive heap profile. If you're building applications with any of those low-level programming languages, Valgrind is a must-have. Besides cache grind and massive, I haven't heard of these two. Obviously, Valgrind I've heard of and used. It comes bundled with valuable tools like Hellgrind. Never heard of that. Hellgrind? That seems familiar, but I don't know. Yeah, these I haven't used. Each of these easily accessible with the dash tool argument. At the risk of yet another spoiler alert, here are some major commandments developers should abide to after reading this paper. Memory is thy new bottleneck, for CPUs have gotten faster, but memory did not. Thou should know thy cache hierarchies. Thou must remember that data locality is everything. Threading does not automatically mean faster code, and remember that thou and thy compiler cannot be physics. So all that is stuff I'm very aware of. This month's library paper, Whatever Programs Should Know About Memory, is available on the author's website, and needless to say, should be another mandatory reading for all of us, as explained by Peter Cords on a question answered on Stack Overflow. This paper is still very much relevant, although many examples shown therein are, of course, based on well-known CPU architectures in the 90s and early 2000s. If you're still interested about computer memory, in particular about its security aspects and how security enforcement agencies can gain access to whatever you're doing on your computer these days, we must not forget to recommend The Art of Memory Forensics by Michael Hale Lai, Andrew Case, Jimmy Levy, and Aaron Walters, published in 2014. The authors of this masterpiece have also published Volatility, a Python toolkit for memory forensics. The book has chapters on Windows, Linux, and Mac memory architectures, including explanations of memory layout, including bits and pieces of C programming. the layout of the data structures in memory, and so many other subjects that we would need another article in this section just for. Cover photo by the author. What's interesting is like my interests in computing are drawing me towards security. Not because I have an interest in security necessarily, which I obviously do have an interest just as a user of computers, and someone who values security, but I don't necessarily have a direct interest in learning about viruses or malware or any of that type of thing. But my interests are pulling me in that direction because I don't think anyone really learns about these low-level things unless they're applied towards something practical like security. Like, I want to learn about these things because they're how computers function at a fundamental level. But it seems like most people learn about these things because of their application towards security threats. But I don't really have like a huge interest in like either writing malware or like understanding malware, reverse engineering it. I just want to understand how computers work and how programs work and be able to manipulate them and contain them and control their behavior. Like, those things I feel like are valuable outside of just the study of malware and computing. But it seems like malware is like the big 1,000-pound gorilla in this space of understanding how computers actually work. When was this published? I'm going to skip this one. Just because it seems like it's going to be very focused on the security aspects. Is there a table of contents? Well, not here, but oh yeah, you can view extended table of contents here. Okay, let's just read the table of contents. They do cover segmentation, which is interesting. How old is this book? When was it published? Is the date? No. Alright, well, we'll try to find it on Amazon, I guess. Alright. 2014, okay. And it's 1,000 pages, wow. Wow, it goes to data structures. Okay. And then they cover their own framework. Let's see if we can find a YouTube.
I'm writing a paper on them. This is a lasting sign between me and...
Hi there. Welcome
Are
to
you AI?
MCSI.
Yeah, you're AI. Okay. It's a playlist.
Going on, we will carry on with the
I just want a really quick introduction of like what its capabilities are.
we have just started. The video today is about volatility, which is a memory forensic tool. If you want to perform memory analysis and forensic, you will use volatility, and this room is highly recommended for you to get started. And the image here. So basically, as I said earlier, we will be using volatility to analyze a memory dump taken from a virtual machine. Okay, and we are tasked to find what is the malicious process that we're running on the system at the time of taking the capture. So you put the malware to how to analyze ransomware with previous. Let's get started. So basically, as with the previous video, I have just we talked about how to analyze ransomware with volatility.
So do they get the memory dump by like reading from, was it kmem? Proc kmem? K and mem. Okay. Kcore, not kmem. Devmem. That's what I wanted. So I was confusing it. Proc kcore with devmem. I said proc kmem. Raw access to physical memory. Historically, it was the entire memory image, but modern kernels heavily restrict it. You typically cannot read all RAM anymore, only certain regions. And then proc pibmem, obviously. VM core. Full memory dump of the system at crash time. Okay. Proc VM core. Dev mem. It's by Microsoft, but it's for Linux. So it uses kcore. Lime is a module, kernel module. So it seems like Lime is like probably the best option, is to get on the system, compile a kernel module, install it into the kernel, use that to dump the entire system memory into a file on the network or the file system. The other alternative is like if you can operate at the hypervisor level below the virtual machine, like being able to take a memory snapshot of the entire virtual machine at the hypervisor level, I think would be another solution to the problem. But obviously, if you're running on bare metal, you're not going to be able to do that.
In this video here, as you can see, I have started volatility by running the tool on the image here. The image name is critics.vmem. VMEM means that this image is or belongs to a virtual machine. Okay. It's taken from a virtual machine,
So
not
level.
a regular Windows system or Linux. It's a virtual machine, but here we ran volatility-f critics.vmem image info to find a speculation about the operating system. Now, volatility has given us Windows XP Service Pack 2, Windows XP Service Pack 3,
That's old.
only 2. So we're gonna go with the first, let me make this bigger. Okay, we're gonna go with the first, okay, it doesn't work. Okay, the first speculation, Windows XP Service Pack 2 x86. All right, so after guessing and finding the profile of the image, we will, as we did earlier, list and display the processes running, or the processes that were running on the system at the time of taking the capture. So we will do the same command, but instead of image info, -- profile equal, the profile name was win xp. Let's copy that.
He tried to hit Control C, which killed his. Is he gonna do it again? No, he's gonna type it in. Okay. He did a single dash.
6. And then we
instead of a
type
double dash.
index list.
Okay, I was happy with
So
that.
we want to see the running processes at the time. So here's saying
Oh, because he did PID single dash.
error in the invalid PID profile. Win XP Service Pack 2 x86.
This guy,
Win
man,
XP
he's a
Service
clown.
Pack 2,
Dude, you forgot the
x86.
fucking
Oh,
dash.
so we have here we forgot the dash.
The Control C and then the
So
deleted
these are the
dash.
processes that we're running at this time of taking the capture. And as I said earlier, it takes time to just get yourself familiar with every process so you can minimize the time taken at the analysis. But as you can see here, we have this one stands out. These processes are part of Windows, Reader stands out, and ALG stands out. So in order to get familiar with every process, we can just use Google to find more information about this process.
Okay.
So here we type, for example,
I just wanted to get a quick feel for like how the tool operates. I don't want to go too deep into it. Let's continue reading past here. A lot of this is Windows focused. And there's a whole section on Windows memory forensics, which is no interest to me. Yeah, this is all Windows stuff. No, thank you. Linux memory, here we go. Okay, so it actually talks about like mem, kmem, ptrace, modern acquisition, fmem, the lime Linux memory extractor, kcore, volatility Linux profiles, elf files, is very much focused on security stuff. Okay. I mean, they did have a really good section on Windows, or on Linux, I should say. So maybe we just put it in the queue here. Books. We'll say the art of memory forensics. Okay, let's go ahead and close that out. Okay, cool. LD, how to create a statically linked position independent executable ELF in Linux, which is what the Go toolchain does. I've never seen that before. Yeah, no, it's that. Does Pi require an interpreter? I think it does, because it has to do some work to figure out where to actually load the Pi executable. It has to do some sort of relocations on it. So I think you have to have a dynamic linker as the interpreter. Dynamically linked, not stripped. I guess that's not the case. Hey, it's that dude again. Okay, we can pop the stack on that one. Old woman that drives you. Hello. Alright, I don't need to read about that anymore. What was I reading about here? This is, how is the address of the text section of a Pi executable determined in Linux? Is there an accepted answer? No, doesn't look like it. You have been blessed with my presence. Thank you for your presence, old woman that drives. Are you indeed an old woman that drives? Alright, I don't want to read any more about this. Security, what is this? How to test whether Linux binary is compiled as position of code. I don't care about that. Why does Linux randomize the address of executable code segments? Okay, I'm done with that. Sorry, state. Yeah, we already read that. Okay, cool. So I'm just gonna go. The old woman that drives says, "Do you know how to center a div?" I do not. That is an impossible task. What am I doing here? I did read a couple of blog posts I should probably record before I move on here. What? Oops. Go to my history here. What was it called? I already recorded that one. It was this guy. I am a fool. I am a fool. You got me. It's kind of a weird name for a blog post, is the name of the author of the paper instead of the title of the paper. Because it makes it think like, oh, you're going to be talking about the person, but it's actually talking about the paper. So, let's see. Published October 6 in issue 85, Memory Management, part of current volume 8. Okay. Oh, alright. I'm done with all this. Bam, bam, bam. Get status, get DC, and we'll just say get CI. Add a bunch of stuff related to memory. Okay, get push all. Is that a NASA logo I see on your name there? Do you drive a rocket ship? Let's go over here. Alright, I need a break for lunch and do my cardio. So I'm going to mark this as check. And I think when I get back in the afternoon, I'm going to do more reading on this Learning Linux Binary Analysis book. We're on chapter 3, which is on ptrace, and we got to page 61. So I actually found the PDF for this, so I can actually read it on stream. Learning Linux Binary Analysis. There was a PDF just like hanging out on Google here. So I'm going to download that if I haven't already. Let's see. Download. Hey, look at that. The site is this. Come on. Download insecure file. It's just because it's not over TLS, it's unhappy. Who cares? Alright. So I think this is the full PDF. Yeah. So if you go up here, we are in chapter 3, 61. So this would be nice because I can copy the code easier from the book without pulling in. Let's go to the repo without pulling it in from the source tree, which is very limited. And I can also read it on stream and y'all can follow along. So I'll be doing that when I get back. I'm gonna break here, take about an hour in a little bit for lunch, and then I'll be back in about hour to an hour and a half to resume reading on that. Cool. All right. I'll be back later. Bye.